Okay, so let's get started. So first, let's review a little bit of what we did last time. So we focused last time on defining our first real computational problem involving MDPs. And we asked what a solution to an MDP should look like. And we said that one possibility might be an open loop plan, which is a fixed sequence of actions. But we soon saw that that doesn't really make a lot of sense because if the world is stochastic, following a fixed sequence of actions can be quite ineffective given that the world can change in ways that you can't predict beforehand. So what that meant was that we wanted to define a new concept as being a solution to an MDP, and we talked about using the notion of a policy. And there were two types of policies. One type of policy was a non-stationary policy, which basically, for every time to go, so when we're dealing with non-stationary policies, we're typically going to be in a finite horizon setting. So for every time to live and state, we assign an action. That's what a non-stationary policy is. And this is an example. If there's only one time step to live and we're in S0, this policy says we're going to take A1. If there's three time steps to live and we're in a S0, then the policy says we're going to take A0. A stationary policy is just a policy that does not depend on the time to live. It just depends on the state, and we'll see where this comes into play later on. So basically, we're looking for policies as a solution to an MDP. But what kind of policy? There are all kinds of policies. How do we choose among all of them? And intuitively, we want to get a policy that gives us a lot of reward, right? That's the main, the main intuitive thing that we would like to have of a policy. And that's not quite enough, though, because there are many ways to quantify how much reward a policy can get. And so last time, what we did was start off by talking about one particular way of quantifying the accumulation of reward in the finite horizon setting. And so in the finite horizon setting, we assume that there's an agent, and the agent knows that it has h time steps to live. H is something that we often call the horizon time. And we went through the little argument last time about how when you're in a finite horizon setting, you need to be using non-stationary policies in order to get optimal behavior. And this is because the best action to do can often depend on how long you have to live. For example, we said that you may not be sitting in this class right now if you knew you only had a month to live, but you're not making that assumption. You're assuming you have years and years and years to live, and you're hoping that by sitting in this class, it might pay off in your distant future. We'll hope so. And we gave some examples. And then we finally defined the formal definition of the value function. So we write v pi k to stand for the finite horizon. So if you have k time steps to live and you're in state S and you follow policy pi, what's your expected total reward you're going to get, right? And Remember, after k steps, you're all done. You're going to get 0 reward after that because this is a finite horizon setting. And we actually wrote out the equation for this. Okay, so after you follow pi from s for t time steps, what's the reward you get at time step t? That's what r of t is. And you can see that the k horizon value function is just the accumulation of that over for k steps. Finally, what we did at the end of the last class was talk about these two computational problems, policy evaluation and policy optimization, where policy evaluation corresponds to just computing the value function for a particular policy, right? And you would compute the value function for all times to live k up to the horizon. So that just tells us how good a policy is, which is useful, but we're often going to be more interested in policy optimization, which is the second problem. And this problem says that we want to learn the optimal policy, which we'll see is equivalent to computing the optimal value function for a particular horizon. So policy evaluation turned out to be fairly straightforward. We said that we can always initialize. So when you have 0 steps to live, the value function when you have 0 steps to live at S1 through S4, so we're assuming there's only 4 states in this problem, we would initialize it to 0. And given the value at time 0, we can try to compute the value when you have 1 step to live. And what's that going to be? Well, let's consider what that value is going to be for this particular state that's being highlighted here. So what we can do is we can consider, let's pretend that the policy with 1 time step to live in this state S4 is this orange action. It suggests this orange action. And the orange action goes to S1 with 70% probability and S4 with 30%. The total value, expected value at this state for this time step is going to be the reward you get for taking that action. This is the immediate reward, plus sort of the expected value of the reward you get after 1 step. And if you had 1 step to live here and you take an action, you're going to have 0 steps to live. So the expected value of v is 0 after taking this action. And that, of course, is just going to be the reward. And you can do the same thing for all of these actions. And you can keep on going back and compute v2 in terms of v1, and so on and so forth, until you go out to the horizon that you're interested in. So this is a very simple procedure, and we talked about the computational complexity of it. Basically, every iteration, well, you've got to do capital H iterations, where H is the horizon time, right? 1, 2, 3 in this case. And for each iteration, you're going to have to go through all the states. So that was n. N was the number of states. And for each state, at each time step, you have to consider potentially all the states that could be reached when there's 1 less time step to go. And that's another factor of n. So we said the complexity was hn squared. And this is just showing you the equations that we discussed last time. All right. So we left off alluding to how you would do policy optimization, but we never quite finished that. So today we're gonna finish that up. And as I said last time, the key thing, one of the key operators in MDP theory is something called the Bellman backup operator. The Bellman backup has a lot of nice properties, and it's the basis for why a lot of the algorithms for MDPs work, and actually the basis for why a lot of the reinforcement learning algorithms work. For example, Q-learning. So a Bellman backup can be thought of as follows. So suppose that we know the values of all the states when there's k time steps to go, right? And this is kind of a valid assumption because we know the base case is with 0 time steps to go, and all these values will be 0 then. So now how do we compute the value of k plus 1 steps to go at state S? Well, we can ask ourselves, what would the value be if we were to take action A1, right? And that would be the immediate reward for taking action A1 plus the expected cumulative reward after you take A1. And that's going to be the expectation of VK for the states you end up in. In this case, we're going to have 0.7 times VKS1 plus 0.3 times VKS4. And then you add on the reward. And you can do the same thing for the other action, right? So if I took this action, how good would it be? And since at state S we have an option, like we're doing policy optimization now, we get to choose what action to take. We have an option of which action. We're just going to take the action that looks best to us or has the highest expected reward according to these formulas. And so VK plus 1 at S is going to be the max of these two possibilities. So this line of reasoning with this Bellman backup immediately suggests, an algorithm which is very similar to our policy evaluation algorithm. So we're going to start off with V0, 0 time steps to live. All of these are going to be initialized to 0. Now with 1 time step to live, we can consider one of the actions. Here the orange action reaches these states and has this value. We can also try the yellow action, and we see that it reaches these states and has this value, right? And then this is just the max of those two, and so on and so forth. So basically, value iteration for the finite horizon case is nothing more than applying a Bellman backup sort of repeatedly and in a particular direction. So going from 0 time steps to live to h time steps to live. Now, what we computed here just assigned a value to every state. But what we can notice is that really we implicitly are getting also a policy for each state, because the Bellman backup implicitly was asking us to maximize over, in this case, the two action choices that we had. And we can simply take that max as being the policy value for every state and time to live. All right, so one thing to notice is that we were able to avoid the exponential complexity of trying to optimize a policy, right? By exploiting the Markov property, which allowed for a dynamic programming approach. And here we have the equations for value iteration, finite horizon value iteration. Pretty much what you would expect. Basically, you have the immediate reward. So we're going to say the value at state S with k time steps to live, the optimal value, is going to be, we'll consider all the actions and we're going to max according to the actions, what the reward is going to be, plus the expected value of the state we end up at after we take this action, but with one less time step to live. So this is the form, this is pretty much the form of the standard value functions in MDP research. You have an immediate reward plus a future reward. And of course, you can extract the policy in the same way by just taking the argmax of this expression, where the argmax returns the argument that achieves the maximum value. If we were to consider the complexity of value iteration, we can just look at the graph, and I think that's probably the easiest way. So let's go back and look. So basically now we have to do h iterations, where h is the horizon time. And for each one, we have to cycle through all the states, right, to assign their values and their policy. And for each state, we have to consider each action. So for each action, we have to consider all the states potentially, like averaging over all the states with the corresponding probabilities dictated by the transition function. So that's going to give us h times n times the number of actions, m, and then for each action we get another factor of n because we have to sum across all the states possibly. So that's where we get this complexity here. H times m, number of actions, times n squared, number of states squared. So we might brag about this because it's polynomial in the number of states and actions, actually linear in the number of actions in the horizon. Do we consider this to be good? Well, this all it's in the eye of the beholder. So it's good if your MDPs have moderately sized state and action spaces. But for MDPs which effectively have infinite state and action spaces, maybe this is not so good. Or even exponentially many states and actions. So we'll see how to deal with those large problems later on, but it's also reasonable to think that value iteration does have practical implications, and that if one wants to, you can actually apply it to very large problems with millions of states. And the nice thing is that you're going to be guaranteed to get an optimal solution, right? Which is something that a lot of techniques today can't possibly address. All right, so in summary, we've been talking about the finite horizon setting for MDPs, and we showed you how to use dynamic programming to compute the optimal value function and the optimal policy in that setting. It's worth thinking about whether or not the optimal policy is unique. It's going to be true that the optimal value function is unique, but what about the policy? Well, if you think about it for just a little bit, you'll realize that optimal policies do not need to be unique. In other words, you can achieve the optimal value in different ways, and just think about what if we're standing at one corner of the room and there's a pot of gold at the other corner of the room. Well, you could walk, and let's say that there's something that's blocking a straight path to the gold. Well, you could walk either way, around the right side of the blockade or the left side of the blockade. And let's assume that they're effectively the same in terms of cost. Uh, that just shows you that there's two policies that can achieve the same value, and that's a particularly simple case. There can actually be, and you can create domains where there's exponentially many optimal policies. All right, so that's all we're going to do as far as finite horizon MDPs, and most of the work, actually deals with the infinite horizon case. But I think the finite horizon case is actually interesting, partly because it is relevant to some applications, but also it builds up our intuition about how dynamic programming can be used to solve some of these problems. And we're basically going to extend that to the infinite horizon case now. So, previously we considered the finite horizon value as our definition of what optimal value is, and we showed how to solve for an optimal policy. Now we're going to consider infinite horizon discounted value. And here, we're not going to limit the horizon, as the name suggests. And let's consider this simple example. So here we see we've got a very simple MDP, and I'm not showing you any rewards yet. But what if we have this reward function? What do we see? What's going to happen here? So if we're in state 0, taking A1 in state 0, if that was your policy, you would just get 0 reward, right? Even if you're running it for an infinite amount of time. Now, A0, on the other hand, you're going to get 0 reward for taking A0, but if you end up in S1, well, you could either take A1 and, wow, get a reward of 1 every time. Right? And similarly, if you take A0, you'll get a reward of 1 every time, but you'll likely end up back there. And so this can be a bit problematic, because taking action A1 actually could give you an infinite sequence of rewards of 1, which in the infinite limit gives you an infinitely large value. And that doesn't seem very, very good, because this is a tiny MDP and we're already seeing that things are breaking down. Yeah, this is an example of a policy that has an infinite value, right? In both of these states, because if you take A0, eventually, in state 0, eventually you're going to reach S1, and then you're going to have infinite value. That's no good. Well, let's look at one more example. So in this case, we don't really have a problem, because if you're an S1, this policy is going to select A0, and with a reasonable probability, you're going to end up in S0 at some point, in which case you're just going to collect 0 reward forever. So there's no infinite values in this case. All right, so what have we done? We've said that if we define the value function in the infinite case as just the sum of rewards over time, the expected sum of rewards over an infinite horizon, we can end up with problems because many or all policies have infinite expected reward. And that makes it hard to actually compare policies, impossible to compare policies. But this seems counterintuitive, because you might have a policy 1 that manages to get a reward of 1 every time step, and then another policy, pi2, that gets a reward of 2 each time step. And policy pi2 is clearly better than pi1. But if we just look at the accumulation of the reward, they're both diverging, and we can't tell the difference. So what's the trick? What do people do? Well, a very, very common thing to do, there are a couple of other tricks that people will do, but a very common one is to introduce the notion of discounting. We're going to say, okay, those rewards that are way out in the future, from where we currently are, we're going to discount them and not worry as much about them. We're going to put more weight on immediate or nearby rewards. And so instead of having this straight out sum of rewards that we have above, we're going to have a discounted sum of rewards as follows, where we have this discount factor called beta, which is less than 1, greater than or equal to 0, that we increase the power of beta as we go ahead. So since beta is less than 1, beta squared is going to be less than beta cubed is going to be less than beta squared, and so on and so forth. All right, and if we want to look at the equation form of this, we can see that the value function of pi, right? So value functions are typically of policies. The value function of pi at s is just the expected value of the infinite discounted sum of rewards if you start in state s and follow pi forever. Okay, so we can see that under this definition, we can bound the maximum value at any state for a policy. And we can do that by looking at this expression and replacing r of t with the maximum possible reward that you could get in a domain. And we're always assuming there's a maximum possible reward. Rewards are bounded. So replace that, and now R max is a constant, and it can come outside of the sum and the expectation, in fact. And then we're just left with this infinite series summation, which we're all pretty familiar with, most likely, and that simplifies to 1 over 1 minus beta. And so this is always going to be a finite value, provided that beta is greater than 0 and less than 1. Right? So that's those are really the conditions on beta. And how do people motivate the use of a discount factor? Honestly, is a very convenient choice mathematically. These exponentials sort of work out nicely in a math sense. So it just simplifies the mathematician's life. Another more morbid interpretation of beta is as a probability of death. So this is a fun exercise to work out if you're so inclined. But imagine a model of the MDP where we're actually going to look at total undiscounted cumulative reward, but we have a probability of death, let's say P, okay? And that's going to be a probability of death at each time step of P. And whenever you do die, you're going to get 0 reward thereafter. And so basically you can look at what's the expected total reward if I sum up all the rewards I collect following a policy until I die, right? You have a probability of death that's equal to P at every step. So what you can show is that model is equivalent to using a discount factor of 1 minus P, or 1 minus the probability of death. And so this makes sense. So suppose that your probability of death is very, very small, close to 0. That means you're expecting to live a long life, and you're going to be willing to pay for rewards that you're going to get in the future, and even far in the future. So probability of death of close to 0 has that property. And likewise, 1 minus the probability of death, which we said is the discount factor, is close to 1. And so when a discount factor is close to 1, that means it also cares more about the future. This theory has been around for a long time, and what Howard showed in the 60s was that given this infinite horizon discounted setting, there's always going to be an optimal policy, right? So that's one of the first mathematical questions you would ask. Does there always exist an optimal policy, or is it somehow, and here we're saying an optimal policy is one that is better or as good as any other policy across all states, right? And so that's a pretty powerful thing to have your hands on. And there is a question of, is there always an optimal policy? Because perhaps there's a problem in MDP where all of these high performing policies are sort of incomparable in that one policy is better than the other in state 1, but the other one's better in state 2, and there's no policy that dominates everything. But Howard showed that one always exists. And further, there's always an optimal stationary policy, as opposed to the finite horizon setting where we had to consider non-stationary policies. This kind of makes sense. If today I'm here in this state today, and I make a certain decision, and then tomorrow I'm in this exact same state, and like yesterday, I have an infinite horizon ahead of me. So both situations, you have an infinite horizon ahead of you, and you're in the same state. There's no reason to change your decision, right? It's not like you've lost one time step to live. You always have infinity in front of you. And so that suggests that you can get away with stationary policies. And just as some notation, it is very common in the literature to see V star being used to represent the optimal value function. And that means that the V star is the value function of the policy pi, where pi is an optimal policy itself. So just as for the finite horizon case, we're going to consider two computational problems for the infinite horizon discounted case. Policy evaluation. You give me a policy and I compute the value function. Or optimization. You give me an MDP and I'm going to compute the optimal policy and the optimal value function. And so we're going to consider these in turn. And I think this is a good stopping point before we hit next lecture. We should be able to finish the two of the basic algorithms next lecture. And we'll go from there.